Okay, so moving on to the next problem on our reactions. We have here a beam supported by 3 external reactions and then a single internal reaction. So here it involves several external reactions, and of course we would like to check our stability and determinacy of this beam. So we are going to count now the reaction. R is equal to, all in all, we have 4 reactions, and then the internal reaction coefficient is 2 for a roller. So comparing now RC plus 3, R is 4, this is 2 plus 3, and we have here 4 is less than 5. So we can say that this is unstable. So meaning the available reaction or the available equation exceeds the number of unknowns. However, if this is the case, we can still manage to solve for the reaction because, as I have said, the number of equation exceeds the number of unknowns. So this is the number of equation we can form, and this is the number of unknowns. So there will be an excess equation to solve for the 4 unknowns here. So if we try to separate both, of course, the principle, when we have an internal reaction, of course, we are going to separate those ones and start where will be the most convenient FBD or free body diagram. So if this is CD, it's actually involving a 2 reaction here. So I'm going to label this as internal RC, and this is an external RD. So for the other beam, we have this to be RAY, but RAX here is obviously 0. Okay, we are going to place here the loading. This is 20, and we have here 40. We have here a roller. See, this is the roller. This is RB. And then the same RC will be applied here. Okay. So from this equation, actually, I would like to point out that there is no horizontal force here. If there is no horizontal force, therefore there will be no horizontal reaction on the beam. So if that is the case, if there is no involved horizontal force, therefore this is equal to 0. Okay. So what makes this beam to be unstable? Because if there will be a horizontal value here, there will be no reaction to counter this. Okay, because this is just a roller. It just is just involving a single reaction that is vertical. However, there is no horizontal force. So therefore, if this is 0, therefore roller still, internal roller still feasible for this beam. Okay, but if once that there will be a value for this horizontal force, there will be no other loading to counter that, and that makes it unstable. Okay, so moving on, of course the most convenient here is this CD. So we are going to express now our distributed load in terms of its resultant. So this is 2 times 20, this is equal to 40. Okay, so we have here a 40, and then also here we have 20 times 2, that is also equal to 40. So we place now the distances. This is 2, 2, and this is 1. This is 1, 2, and this is 2 meters. So we first work with the simplest at CD. So from FBD of CD, we'll just take moments at C. We have clockwise 40 times 3, and then a counterclockwise RD, that is 5 RD, so this is equal to 0. So therefore RD is equal to 120, or 40 times 3, that is 120, divided by 5. We have equal to 24. Okay, so the other internal reaction, we will just take moments at D is equal to 0. We have a negative rotation, negative 40 times 2 plus 5 RC there is equal to 0. RC is 80 all over 5, that is 16. Okay, so our check mechanism, we have reiterated that we check it by this summation forces vertical is equal to 0. So all of the upward forces are RC and RD. We have 24 and 16 is equal to the downward forces, that is equal to 40. Is it really equal? Of course, if you're going to add this is really equal to 40. So upon that checking, we are now sure that these obtained reactions are correct. Okay, so proceeding to the other free body diagram, that is free body diagram of ABC. This is ABC. We just have to transfer what we have obtained on this one. So I'll just place the value of RC, which is equal to 16 here. Okay, and then proceed to the FBD of ABC. Okay, so we take moments at summation moments at A is equal to 0. We have 40 times 1. Okay, half of 2 is 1. And then plus 40 times 2, this concentrated load, minus 4 RB, 4 RB, okay, plus 16 times 5. So therefore, RB would be equal to 50. Okay, 50. So by and by, we're going to check our result first. So next, we have summation moments at C is equal to 0. Sorry. Summation moments at B, I should say, because we are after with RA. We have 16 clockwise moment minus 40 times 2 minus 40 times 3 plus 4 RA is equal to 0. So we have a value for RA equal to 46. So checking now our reaction by this summation forces vertical is equal to 0. All of the downward force, we have 40 plus 40 plus 16. Is this equal to 50 plus 46? So if we are going to add 40 plus 40 plus 16, that is 96. And it is really equal to 96. So therefore, we are now quite assured that our obtained reaction is correct. So this will be now the reaction for this problem. Okay. So let us move on to the next problem. So for this problem, a simply supported beam, of course this is just a warm-up for us. I'll just get the resultant here. So this is 20 times 5, and 20 times 5 is equal to 100. Okay, and then we have here two vertical reaction. Of course, the horizontal reaction here is 0 because there is no horizontal force to be countered by that. So just have to label this as RA, and that is RB. So just the same, we are going to perform this summation moment A is equal to 0. So we have 100 times 10 minus 20 times RB plus 20 times 25 is equal to 0. We have an RB of 75 kilonewtons. So for the other reaction, we are going to take moments at the other support. Summation moments at B is equal to 0. We have 20 times 5 minus 100 times 10 plus 20 times RA is equal to 0. We have RA equal to 45 kilonewtons. So if you're going to check our reaction, this from this summation forces vertical, we have downward 100 and another downward 20. So is this equal to 75 upward and another 45 upwards? Okay, so this is 120. So I think this is also 120. So it is really equal to 120. So therefore we are now assured that our reaction here is correct. Okay, moving on to this next problem. This is a trapezoidal load. So basically you need to divide this into its composite area in a way that it is a triangle or a rectangle. So one option is divide this into rectangle and triangle, okay? Or you might want to divide this by two triangles, okay? So I prefer to divide this by two triangles so that we can know the location of its equivalent resultant. So for the resultant of the larger triangle, I'll just resolve that one on the center of gravity that is located, this is 2 meters, okay, from the height. So that is the location of that. And then just apply the triangle formula, 1 half 90. 90 by 6. Okay. So we have 270. Okay, so similarly, I'm going to resolve the other triangle on its centroid 2 meters from the height. Okay, so I'll just apply again the triangle formula, 1 up 30 by 6. I think this is 90. Okay, so we take summation moments along A is equal to 0. We have 90 times 2 plus 270 times 4 minus RB times 2. So by the way, we just forgot to place here the reaction. This is RA and RB. So horizontal force here is 0. Okay, so the excess here is 4. Okay, the pair of 2 here is 4, and the other side of 2 here is also 4. So that is why that is 270 times 4. Okay, so solving for RB, we have so I think we have to replace this by the correct distance. 6. This should be 6, so that this is 210 kilonewton. Okay, so we take moments at the other support, summation moments at B. We have negative rotation 270 times 2, another negative rotation, negative 90 times 4 plus 6 RA is equal to 0. So RA therefore is equal to 150 kilonewton. So by checking, so again we will use this one two downward forces, 90 and 270. Is this equal to the two upward forces, 210 plus 150? So I think this is 360, and this shall yield also to 360, so it is really equal. Therefore, we satisfied a balance on summation forces. Vertical is equal to 0. Okay, moving on to this next problem. Again, we are going to establish its free body diagram. So first, a horizontal force here is 0. This is RA, and this is RB. So we take moments at A is equal to 0. We have 500 times 5 plus 800. Okay, so let us resolve the resultant here. So 50 by 10, that is equal to 100. So that is plus 800, and then clockwise plus 100. The distance is 5 plus 3, 8 plus 8, 16 plus 5, that is 21. 8, 16, 22. Okay. Plus 13 plus 8, 21 plus 5, 26. 26 RB is equal to 0. Okay. So RB is equal to 207.69 kilonewton. So anyway, we will just check this by summation force is vertical by and by. So summation moments B is equal to 0. Negative 100 times 5 plus 800 minus 500 times 21 plus 26 RA is equal to 0. So RA is 392.31 kilonewton. So our check mechanism is this summation forces vertical is equal to 0. So the downward force is 500 and another 100 here. Is this equal to the upward force? 207.69 and 392.31. So this is 600. Is this also equal to 600? So we have also 600. So therefore, again, our reaction is ensured, okay? So next problem, we have a simply supported beam this time. This has a pop-up. Anyway, we'll just place there. Of course, this is obviously 0. And then this is RA. And this is reaction at B. So summation moments at A is equal to 0. We have 8 times 8 minus 40 minus 24 RB is equal to 0. So therefore, RB is equal to 1. So the other reaction, we have summation moments at B is equal to 0. We have negative 8 by 16 plus or minus 40 plus 24 RA is equal to 0. So RA is equal to 7. So RA is equal to 7. So by inspection, we can see that we have a balanced force at the vertical, because we have a downward 8 here and an upwards 1 and 7. So that is our check mechanism, and we found out that we have a correct reaction or calculation for our reaction. Next. So we have here another simply supported beam. So this is just a warm-up for us. We have here two reaction. Of course, this is 0. And this is RA. And that is RB. So this is the resultant 6 by 8. This is equal to 48. And then taking moments at A, we have 8 RB. This is negative rotation plus 48 times 12. Now this is equal to 0. We have RB equal to 72. And then for the other reaction, summation moments at B, we have 48 by 4 minus 8 RA is equal to 0. We have an RA of 24. So check mechanism, summation forces vertical. We have upward 72 plus 24, and then equate it to the downward. Is this equal to 48? So it is not equal to 48 because obviously this will exceed. So where is our mistake here? Okay. So we have to check again our equation. Moments at B, summation 48. And then I think, ito na, dapat yan plus. Okay. So if that is plus, therefore, our result here shall be equal to negative. So 72 minus 24, yeah, really, that is equal to 48. Check. Okay, so you see how important is our check mechanism. We can now ensure that our reactions are correct. Next. So first, we illustrate the free body diagram. So this is the beam. we have here reaction. I think I'll just express this now into its component. So I think this is 60, or if this is CD, therefore this is CD sine of 60, and this is CD cosine of 60. And then we have here the component also of 260. First, for the vertical. So the vertical, of course, we need to complete the triangle here. For the vertical, we'll just have to refer to the vertical slope, 12, and then divide it by the hypotenuse, and then multiply it by the mother force. And then similarly for the horizontal, we refer to the horizontal, 5 over 13 of 260. Okay, so we have here RAY, and this is RAX. Okay, so by that, you're now ready to take summation moments. Summation moments along A is equal to 0. We have 12 over 13 of 260, this one, times the moment arm, that is equal to 6, and this is 4. Okay, so multiply it by its moment arm, 6, and then minus CD sine of 60 times 10. This is equal to 0. So therefore, tension at CD is equal to 127.91 kilonewtons. Okay, anyway, we'll just check that one by and by. Summation moments at B is equal to 0. We have think from D, okay, from D we have negative 12 over 13 times 260 times moment arm of 4 plus 10 RAY is equal to 0. So RAY is 1296. So before we proceed, let us check our vertical forces. So first we have downward force equivalent to 12 over 13 of 260. So this shall be equated to upward force we have obtained, that is 96, and the other one is CD sine of 60. CD sine of 60. So 96 plus 127.91 sine of 60. We have here 206.77. is it equal to this 12 divided by 13 of 260? 12 divided by 13 of 260. We have 240. So somehow there is a mistake in our solution. Okay, so let us check now the equation. So for the calculation, I think this should be equal to 144. Now if this is equal to 144, then we have this to be equal to, and still it's not equal to 40 if we're going to have this one. So I think this is 166.28, and this is 166.28. Check it again. We have 166.28 times sine of 60. This is 144 plus 96. This is equal to 240. Okay, that is 240. That is really equal to 240. Okay, so therefore we are quite assured that our vertical reactions reaction at the cable and vertical at y is correct. So for RAX, mas madali na lang to. We'll just have summation forces along x is equal to 0. So we have a rightwards RAX, a rightwards component of 260, that is 5 over 13 of 260, minus CD cosine of 60 is equal to 0. Okay, so let us check our equation. RAX is rightwards, that is rightwards 5 over 13 to 60 minus CD cosine 60. Okay, so therefore RAX, just have to replace this by CD. This is 166.28. Finally, RAX is equal to 16.86 kilonewton. Okay, so that's it for the horizontal. So I think we have completed the reaction obtained here. Okay, for the next problem, we have a problem on a symmetrical beam, of course. Symmetrical beam shall have an equal reaction. Okay, so all in all, if we are going to get the result here, this is 16 times 6 is 96. So 96 plus 4, 100 plus 4, that is 104 divided by 2. We have equal to 52. 52 and 52. So we have 52 and 52. Okay? So I think we are done now. We have completed all the problems in your previous quiz. So please stand by for my video on method of joints and method of sections, or in short, that is analysis of classes. So see you soon. Thank you. Bye-bye.